Hello, I'm Seema and welcome to part 7 of the chapter Alcohols, Phenols and Ethers. In this video, we are going to start talking about the preparation of alcohols. Alcohols can be prepared by 3 different sources. The first, we can prepare alcohols from alkenes. The second is that we can prepare alcohols from carbonyl compounds. And the third is that we can prepare alcohols from Grignard's reagents. In this video, we are going to talk about the first method the first source of preparation, that is, how do we prepare alcohols from alkenes. You can prepare alcohols from alkenes by 2 different methods. The first is by acid-catalyzed hydrolyzation, and the second is by hydroboration oxidation. So let us understand these one by one. The first method of preparation of alcohols from alkenes is by acid-catalyzed hydration. Acid-catalyzed. It means the catalyst is an acid. Hydration means addition of water. So acid-catalyzed, the reaction is catalyzed by an acid. And what is the main thing about an acid, which is why do we use acid? Because it's a source of protons, H positive. So the reaction is where addition of water molecule takes place in the presence of an acid, that is in the presence of a proton. So if you have an alkene like you have here, there's a double bond between 2 carbons in a hydrocarbon, and you add water to it in the presence of an acid, that is the catalyst is an acid, you get an alcohol. What happens here is, if you notice, water can be written as HOH, right? Water, you can write water as HOH. So, when the bond breaks, what is the breaking of a bond? The breaking of a bond is the pi bond, it breaks. A bond is made by 2 electrons contributed by each carbon, which are being shared by both the carbons. So when this bond breaks, it means both the carbons, the electrons, they get separated out. And the water molecule breaks here, you get H and OH. To one carbon, the hydrogen gets attached. So when you break this bond also here, the H will get its electron and OH will get its electron. And if the bond here breaks, both the carbons get 1 electron each, right? So what happens to one of the carbons? 1 electron of the carbon, 1 electron of hydrogen will give you the CH, and the other carbon which has this 1 electron and 1 electron on oxygen of OH, it gets connected here to give you OH. And now whatever the compound is, the original hydrocarbon or the original alkene was, you will get the corresponding alcohol, right? Now, what you have to notice here is that this is a symmetrical alkene, the one that we originally took. It is symmetrical means on both the sides of the carbon atom, you see a similar structure. It is not an uneven number of carbon atoms, and the double bond is not present, does not have the same groups on both sides. In this case, it has the same groups, but if it was unsymmetrical, if the alkene was unsymmetrical, what would happen? It becomes important to remember the unsymmetrical, to see how the reaction takes place in the case of unsymmetrical alkenes, because we want to notice whether the addition that takes place, this is an addition reaction, you see, water got added to the molecule. So the addition, whether it is a Markovnikov addition or is it an anti-Markovnikov addition. So what do we notice here? When you have an unsymmetrical alkene, the addition of water takes place in such a way that the second bond breaks. 1 electron comes here, 1 electron comes to this carbon, and with water again H and OH are formed. And we notice that the H does not connect to this carbon, it connects to the terminal carbon. Do you see here? Hydrogen attaches to the terminal carbon and the OH group attaches to the carbon in the middle. That is the carbon which is not in the end. So when such an addition takes place, we call it a Markovnikov addition. What is the Markovnikov? What is Markovnikov's rule, and why are we calling it Markovnikov addition? According to the Markovnikov rule, the negative part of the addendum that compound or that part which is adding is known as the addendum. If you imagine water to be ionic, H will be H positive and OH will be OH negative. So in this molecule, the OH should be the negative part. It is more electronegative. Oxygen is more electronegative. So H is H positive and OH is negative. So this becomes the negative part of the addendum. So Markovnikov's rule says that the negative part of the addendum adds to that carbon of an alkene which has lesser number of hydrogens, right? The negative part of the addendum, which is OH, will add, in this case, the negative part of the addendum could have added to any of the carbons because both the carbons are identical. Both of them, if these are hydrogen atoms, both of them have hydrogen atoms, right? But here, the two carbons are not identical. This carbon is attached to two hydrogens, while this carbon is attached only to one hydrogen and to a methyl group. So these two carbons are different. So according to Markovnikov rule, when the addition takes place, the negative part of the addendum adds on to that carbon which has less number of hydrogens. So we say, in this case, when acid-catalyzed hydration takes place of an unsymmetrical alkene, the addition is a Markovnikov addition, which means you will not get a terminal alcohol. Terminal means the OH group will not be on the last carbon, which already has a larger number of hydrogens. It will be attached to a carbon which has lesser number of hydrogens. So this is to be understood, that how the addition of water molecule takes place and how when water adds on to an alkene by breaking the pi bond, one side is occupied by hydrogen, the other side, the other carbon, OH gets attached to the other carbon, and this addition is a Markovnikov addition. So you understood the basic reaction. Now if we see the mechanism of this reaction, looking at these two, we do not know what is the role of the acid. Why did acid catalyze this reaction? Why was it essential to have an acid? But if we study the mechanism, this becomes clear to us. What was the role of the acid? And second thing that becomes clear to us is, why was there a Markovnikov addition? The addition could have been anti-Markovnikov also. In the second example that will be the method of preparation, we'll see the addition will be anti-Markovnikov. But in this, the addition is Markovnikov addition. So both of these reasons will be explained if we understand the mechanism of this reaction. So let's say, understand the mechanism. In the mechanism, the first step is that hydronium ion, that is protonation of alkene, takes place. Protonation of alkene, proton is positively charged. When a positively charged substance attacks, it obviously attacks the negatively charged part of the molecule, right? And a positively charged substance, when it is attacking a negatively charged part, we call it an electrophilic addition or electrophilic attack, right? So in the first step, an electrophilic attack takes place by a proton. We call it the protonation. The protonation of alkene takes place to form a carbocation. But before the protonation takes place, where is the proton coming from? The acid, right? But is the acid directly going to react? Then what about the water, which is the reactant? The water molecules, which are the reactant, the proton comes and attaches itself to the water to form hydronium ion, H3O positive ion. This H3O positive ion becomes the source of proton, not the acid directly. So first the electrophile is created. And what is the electrophile? The electrophile is a hydronium ion. So H2O gets attached to H positive, or H positive gets attached to a water molecule and forms a hydronium ion. Then this first step takes place where a proton of the alkene is given. A protonation of the alkene takes place. How does that happen? This is an unsymmetrical alkene. I deliberately took this one. So the unsymmetrical alkene is here because I wanted you to understand from the mechanism both the fact that what was the role of H positive, and I also want you to understand why it is a Markovnikov addition. So the second bond here breaks. We know the pi bond is always weaker, so the two electrons, they separate. These two electrons now, H3O positive is positively charged. Since it is positively charged, what will happen? The oxygen here of water molecule, it has one lone pair of electrons, and the H positive, usually in water molecule, oxygen has two lone pairs of electrons. Oxygen has 6 electrons, and let me just show it here. In a water molecule, oxygen has 6 electrons, 1, 2, 3, 4, 5, 6, right? It uses 2 of these electrons to form covalent bonds with hydrogen to form. So these are the 2 bonds, and it has these 2 lone pairs of electrons, right? In the formation of the hydronium ion, when the H positive attacked the water molecule, it is one of these lone pairs of electrons was used up to add the hydrogen to it. Do you see here? One of the lone pairs of electrons of oxygen was used up to add that hydrogen, and that's why the positive charge shifted to oxygen. Hydrogen ion was positively charged, which means, what does positive charge mean? That it had 1 electron less, right? So there is 1 positive charge. Oxygen had a lone pair of electrons. Both the electrons, although they were a lone pair, they belonged to oxygen. But oxygen gave those 2 electrons to hydrogen ion to form a bond with hydrogen. Hydrogen did not have electrons, therefore oxygen provided both the electrons to form a covalent bond. Such a bond is actually called a coordinate bond. So that bond was formed, and it resulted in the formation of a hydronium ion. And since oxygen gave 1 electron in covalent bonding, that does not affect its charge, but it gave the second electron to hydrogen, which was actually its own. So now hydrogen got back an electron, so hydrogen is neutral, but oxygen lost that 1 electron, and therefore oxygen became positive. Now that this is clear, you have to understand what happens when the second bond here breaks. The pi electrons, a pair of electrons, are given to hydrogen. The hydrogen, which had actually taken the pair of electrons from oxygen, oxygen is more electronegative. Actually, why does this reaction take place? Because oxygen is more electronegative, and these electrons are loose. The pi electrons are not very strongly bound. So oxygen, being stronger, says, okay, I gave you 2 electrons. I gave you 1 electron. I'm sharing that. I would like to take my electron back. So oxygen takes back that electron, but this time the pi electrons of carbon-carbon double bond, they provide the 2 electrons to hydrogen to attach the hydrogen. Now what happens here also? Both the carbons, when this bond breaks, 1 electron goes to this carbon, 1 electron goes to this carbon. So hydrogen comes and attaches itself to one of the carbons, any one, we'll see which one, and it gets attached to one of the carbons, but the electron of the other carbon is also used up by hydrogen to form a covalent bond. So that carbon, which lost its electron now to hydrogen, becomes positively charged. Just as oxygen had become positively charged, this time it is carbon that becomes positively charged. So hydrogen, which adds to hydrogen, is positive. And even if you think of Markovnikov, the positive part is adding to that carbon which already has larger number of hydrogens. That is what happens here. So the carbon, if hydrogen got attached to this carbon, the carbon which lost its electron now becomes positively charged, just as the oxygen here had become positively charged. This species is now known as carbocation. This carbocation that is formed, why did the proton add to this carbon and not this carbon? Why did this carbon become positively charged? The proton got added to this carbon, and the positive charge was on this carbon because, according to Markovnikov rule, the positive side of the addendum, the negative part of the addendum, adds to that carbon which has lesser number of hydrogens. But the positive charge will get attached to the carbon which has larger number of hydrogens. That is why the hydrogen we find is adding to this carbon and not this carbon. And this carbon gets a positive charge. So this becomes a carbocation. But why? Why did the hydrogen attach here? Why did Markovnikov say that this would attach here? Why did the hydrogen not go here? Because if the hydrogen would have gone here, then the positive charge would have been on the first carbon, making it a primary carbocation. A primary carbocation means the carbon having the positive charge is attached to only one other carbon. It would have been a primary carbocation. But here, by getting the positive charge on the second carbon atom, the carbocation is a secondary carbocation. And we know that secondary carbocations are more stable than primary carbocations. And chemicals, like all of us, are lazy. They do not want to do extra effort if they don't have to, and it doesn't make sense making an extra. You would rather be stable than go in a position where you're unstable and where you'll have to react again. So it is more stable, although this will have to react because it is charged, and in nature charges don't fly around. It'll still have to react in order to become a neutral compound, but out of these situations, that is whether it was a primary carbocation or a secondary carbocation would be more stable. So the secondary carbocation is formed and the proton is added to the last carbon. As this happens, what happens to the water molecule? The water molecule got back its 2 electrons and it became neutral water molecule, where oxygen, there are 2 lone pairs of electrons on oxygen and the 2 hydrogens are attached to the water molecule. Now the question is that in the reaction, we were talking of hydration, that is the addition was supposed to take place of water. But here until now, water seems to be the catalyst, while it seems that the hydrogen H positive ion of the acid is what is reacting. But that's not true. In the end, we'll find that the hydrogen, that is the proton of the acid, only made the alkene reactive. And now it will help in the addition of the water molecule and the proton will be given out, and that will make the proton a catalyst. So let us see what happens in the next step. In the next step, step 2, nucleophilic attack of water on carbocation. Now the carbocation is positively charged at the second carbon, but the water molecule has oxygen which has lone pairs of electrons, which means it is electron rich, and the carbocation is electron deficient. It has got a positive charge. So electron rich species acts as a nucleophile. It is attracted to positive charge. Electron rich means it has these electrons which it can give. So it acts as a nucleophile. Nucleophile means attracted to the positive charge. So a nucleophilic attack of water takes place on the carbocation. This is the carbocation, the lone pair of electrons on water. They attack the positive charge, that is this carbon. So if oxygen attacks this carbon, what happens is that the entire water molecule, it gets attached in such a way that this was positively charged, which means this carbon has 1 electron less. The oxygen here uses both the electrons to form a bond. Carbon also doesn't have a bond here because it was supposed to, both the electrons of this carbon and this carbon were used to form a bond with this hydrogen. So this is deficient in electrons. The 2 electrons of the lone pair are used to form a bond with carbon. But whose electrons are used? Oxygen's. So the moment oxygen, it is a similar situation. The moment oxygen uses up its lone pair, it has lost 1 electron. Therefore, that part, the oxygen, becomes positively charged. So the water molecule adds in such a way that oxygen becomes positively charged, and this oxygen of course has 1 lone pair of electrons, which I have not drawn here, and it is positively charged, and it gets connected to carbon, the second carbon. Now this is again unstable because it's not a neutral compound. So what happens in the next step? Deprotonation occurs. There is only 1 extra proton here. If you remove that proton, the compound will become stable and it will become neutral. That is what happens. Deprotonation now, since the positive charge is here, it becomes easier for this hydrogen to leave, because hydrogen as it is in a water molecule was happy, but when there is so much of crowd, hydrogen says, I would rather be free in the form of an H positive ion, because there are more acid ions, there are more H positive ions in the acid which is a catalyst. So let me just leave. By leaving my electron, because electron, you keep the electron. I don't need that electron. So it leaves behind the electron, becomes H positive and leaves the molecule. So we say the step 3 is deprotonation to form an alcohol. This hydrogen loses its electron, gives its electron to oxygen. Okay, you take it. You take both of these. Now you have 2 lone pairs. Be happy. I am going. So the water molecule, and what happens to that hydrogen ion? It is H positive. So it goes to the water present in the reaction mixture, and the lone pair of electrons on the oxygen of water now gives its electrons to form hydronium ion again. This hydrogen, now the question is, the situation for hydrogen here is the same. Here also it was attached to oxygen, and in water also it is going to be attached to oxygen. Why did it choose to leave here and go and get stuck in a similar situation? Because this is a bulky molecule. It would be more stable if it went to a smaller molecule. So, or it would be more reactive, it will be able to act more if it was with a smaller molecule. So the H positive chooses to go with water molecule to form a hydronium ion, and at the same time, this now, by removing hydrogen from here, you see in the first step we got hydrogen on this carbon, and in this step, in the third step, we got OH on the second carbon. So we get OH, that is, we get a secondary alcohol. We do not get a primary alcohol. This is Markovnikov addition. The H positive, which was added in the end, that has gone out. So H positive was only a catalyst. In the end, what added to the molecule was hydrogen and OH. So it resulted in the formation of an alcohol, and since it is a secondary alcohol, it proves that this addition is a Markovnikov addition. And the reason also is clear, because the secondary carbocation is more stable, therefore the addition had to be Markovnikov. It would not be a primary alcohol. And even if you did get a little error by some molecules, the yield of primary alcohol will be so less that it would be negligible. You would mainly get secondary alcohol. So that was the first method of preparation of alcohols from alkenes by acid-catalyzed hydration. The second method is by hydroboration oxidation. What is borane? Boration. Borane is BH3. And borane usually is more reactive if it is in the form of diborane. 2 molecules of borane, when they get together, they form diborane. BH3 is 1 molecule. 2 molecules together, it's a dimer. It forms BH3 whole twice. It's just written in this way to show you that one of the hydrogens at each step will be separating out. So it is BH3 whole twice diborane. And you have an unsymmetrical alkene. Again, we are taking an unsymmetrical alkene to show you how this addition, on the other hand, is going to be anti-Markovnikov, not a Markovnikov addition. What happens when diborane reacts with an alkene? This reaction takes place in a few steps, which is followed by oxidation. So you have propene, and when it reacts with diborane, one of the BH3s only reacts. And the other BH3, it separates out, and what happens is that boron would be positive, it attaches itself to the terminal carbon. This looks like a Markovnikov addition. It makes sense. BH3. So the boron seems to be, the BH3 part seems to be positive, but it comes and attaches itself to the terminal carbon. And the hydrogen, this bond breaks, the hydrogen attaches itself to this carbon, and the BH2 attaches itself to the terminal carbon. Again, when the bond broke, 1 electron went to boron, 1 electron went to hydrogen. This bond broke, 1 electron with this carbon, 1 electron with this carbon. With this carbon, hydrogen got attached, and with this carbon, boron got attached. In the next step, there are more molecules, what happens? There still is a lot of alkene in the reaction mixture. So after the first step, another molecule of alkene attaches itself to boron, the BH2 part. And now, out of the BH2, one hydrogen, if you say BH2 are two hydrogens attached to it. Let us say that this is boron, one hydrogen here and one hydrogen here. One of the bonds again breaks in the next step. And when it breaks, one electron goes to this hydrogen, one electron comes to boron. The boron adds on, and when it happens, the hydrogen that is removed from here, again, the second bond here breaks, the hydrogen goes and attaches itself to the second carbon, while the boron attaches itself to the terminal carbon, just as had happened in the first step. So boron attaches itself here and hydrogen comes here. So now you have two of these groups. So you have CH3, CH2, CH2 whole twice. There are two of these groups, and boron now is left with only one hydrogen, right? In the next step, this hydrogen, this bond will also break. This bond between boron and hydrogen will also break. And the hydrogen will occupy the second carbon of the next molecule, and the boron will attach itself to the terminal carbon, resulting in this three molecules of alkene which have got attached, that is propyl group and boron, right? So you get this larger molecule where boron is attached to the terminal carbons of three propyl groups. Now oxidation takes place. Oxidation that takes place is in aqueous sodium hydroxide and in the presence of hydrogen peroxide. What happens here is, in the presence of hydrogen peroxide breaks down into two OH-OH groups. Two groups, that is OH and OH. Both of them are alcoholic groups. So what happens as a result of this oxidation? If oxidation is occurring, oxidation can be described as addition of oxygen. So OH groups, in a way, since oxygen is attaching itself, we'll call it oxidation. So the three bonds with boron will break, all the three bonds, and all the three molecules where boron broke, one of the OH will come and attach itself here, and rather there were three OHs here, they will come and attach themselves to the terminal carbon, and three OHs which are left, they will attach themselves to boron to form boron trihydroxide, right? BOH whole thrice will be formed. Let me explain this once more. You understand this part, that with every step, boron had three hydrogens attached to it. Out of diborane, only one borane, BH3, is reacting. So boron attaches the first molecule of alkene, where boron attaches to the terminal carbon and hydrogen comes to the second carbon. Right? In the second step, another alkene molecule attaches in the same way, breaking one of the hydrogens, and the hydrogen attaches to the second carbon while boron attaches to this carbon. So you again have CH3, CH2, CH2, and which is attached to boron. So we have two of them now. You still are left with one hydrogen. So that one hydrogen will again break down to add to another alkene, and again boron gets attached here, hydrogen gets attached here. Therefore you have three bonds that boron was making initially with hydrogen. It now makes three bonds with three alkene molecules. When oxidation takes place, H2O2 breaks down into two, and in the presence of sodium hydroxide. So you really see, and water molecule, if we do the mechanism, you will know where is the source of all the OHs. But I would like you to just imagine that there are two OH radicals that are formed, and all the OHs, where are they going to get attached? When the boron, all the three bonds break, each of these carbon is now, if the three bonds with boron break, this carbon is already satisfied because it has got hydrogens, the number of hydrogens required, that is, its tetravalency is completed, carbon is forming four bonds, only this carbon has one atom less. So the OH will come and attach to that carbon. And since there are three molecules, three alkenes, alkyl groups, so you will get three molecules of propanol. And the other three OH groups will get attached to boron and form BOH whole thrice. And if you see the addition of the negative part of the addendum took place on the terminal carbon and not on the carbon with lesser number of hydrogens. It added to the carbon with larger number of hydrogens, because initially the number of carbons here, there is only one hydrogen here and there are two hydrogens here. If it was Markovnikov addition, the OH would have added here. But we find that in the end, we find that it is primary alcohol which is formed, which means that this addition is an anti-Markovnikov addition. Right? The reason why I did one video on just these two reactions is that it is important to understand reactions. Once you understand what is happening, which atom is going where, and you kind of make a story out of it, you tend to memorize it better. If you just try to mug up the equations, you have a tendency to forget them. So just try to understand what is happening and repeat it a few times, and then remembering it will not be difficult. During your exams, it will always come back to you. So with this, I'll wind up today's video. If you found it useful, give it a thumbs up. If you want to watch other videos of this chapter, click the link that appears on top of the video. And please spread the message of my channel to your friends, because I would be very happy if the channel helps any child score better marks and to fulfill their dreams in their education. So thank you for watching. Bye-bye for now.